I am recording and it hears me. Yes, okay. All right, hopefully this loads. In the meantime, how's everyone doing? Good? Woo, I like it, yeah. All right, does anyone have any questions? Hopefully this will pick up. If it doesn't, it'll be okay. There were some students that were still struggling with seeing the Fisher projections. So I built the one molecule and I was gonna try to show it to you. Let's try it this way. This usually gets messed up on the recording, so hopefully this makes sense to you while I'm doing it. Okay. All right, so looking at this molecule, trying to get into the Fisher projection, what we're starting with is like this, where I have my aldehyde is down to the left. Oops. So the aldehyde, is up to the left. The alcohol is coming out at me. The amine is at me on a wedge on this carbon, the third carbon, and then I have a methyl all the way on the end. So when we're getting into the Fisher projection, we have to have this carbon chain. It needs to be eclipsed. I need that U shape. So what I have to do is rotate this, spinning it up. So when I spin this up to get it to be eclipsed in the U shape, that's when I see that that amine went into the plane. It became the dash. That's that initial rotation, right? That's what we see here. Then I'm imagining that I'm looking at it this way, like I am positioned right here. So that means that I am taking this molecule and I'm spinning it up, and then I am pushing it flat. So when I push it flat, that's where I see, my amine is on the right-hand side, my alcohol is on the left-hand side, and then my aldehyde is down at the bottom, right? So that is that perspective, because all I did was I went eclipsed, and then I push it flat. That is all my Fisher projection is. So then some students are asking, well, what if I wanted to put the aldehyde at the top? What if I imagine that like my head is here, laying at it, and I'm laying down this way? So then you are just rotating it up this way and pushing it down flat. So now with the aldehyde at the top, your alcohol is on the right, your amine is on the left, and then your methyl is at the bottom. That is still 100% correct. That is an accurate representation of that Fisher projection, right? So that's all the Fisher projection is that we get it to be eclipsed, because that's the definition, it's eclipsed, and then we push it down flat, and then we draw what we see. Does that make more sense now? Does anyone have any questions about Fisher projections? Yeah.
Either
So on the exam, I will most likely, bless you, give you a scaffold where I will put the methyl or the aldehyde, either, bless you, up at the top or at the bottom. So I would force a perspective. The purpose of that is just to make it easier for the TAs to grade, because we have 260 exams to get through in 3 hours. So yeah, it's just a lot of exams to get through. So we have to like limit the variability to make it faster to grade. So then I usually give you a skeleton. It also makes it faster for you to take the exam, because then you're not drawing the whole thing. You're just filling in little blanks. Cool. Any other questions? All right, sweet. So that's all good. We need to unpin me. Do that. Woohoo. All right, so let's finish out our stereochemistry discussion, and I imagine we'll not need the entire time today. If we do, cool, whatever. But if we finish early, then I was gonna start going over the study guide and just start exam stuff. So we're not gonna start any new material. We'll just either finish early and start preparing for the exam, or we'll just spend today finishing out the content, just making sure we fully understand it. All right, that's the plan for today. All right, so we have looked at our chiral molecules, and the thing that we didn't account for yet is the physical and chemical properties that are going to be associated with these molecules. So our enantiomers are going to have identical physical properties. They're essentially acting like the same molecule, but they're going to have different optical properties. So that means that they're going to be rotating the optical activity. They will rotate light in opposite directions. Because they have the same physical properties, they're going to have similar chemical properties. Significance is that that is going to make them difficult to separate. And like I said, sometimes you only want one of the enantiomers. Sometimes you only want the R. Sometimes you only want the S. It depends on what activity you're looking for. So sometimes you want to separate them. You don't want both. And it's going to be like, I can't just do distillation because they have the same exact boiling point. They would boil at the same point. They would become a gas. They would condense, and then you would collect them together. So the way to separate them is by chiral resolution. So how you do chiral resolution, so that is just resolving, meaning separating, distinguishing the two molecules of chiral molecules. So if I start with my R and my S, right? That is my enantiomeric mixture. I add to that mixture an enantiomerically pure compound. So I start by adding in something that's going to react with it that'll add in just one stereocenter. So it's going to be R no matter what. When I do that, that makes RR and SR. What is the relationship here? If I flipped one but not all. They're diastereomers, right? Diastereomers are going to have different physical properties. They're going to act like totally different molecules. So the diastereomers, you can easily separate. They can just go into different bottles based on their boiling point or their polarity or melting point, whatever separation technique you're trying to use. You can separate them, put them into different bottles. So then when I physically separate them and put them into different bottles as diastereomers, all I have to do is now take that chiral resolution agent, that R piece, I just got to pull it back off. So I put it on so I can separate them, and then I pluck it back off to get my R plus R and S plus R to now have them separated. So that's the chiral resolution, is to use the fact that the enantiomers have the same physical properties, but diastereomers have different physical properties. So all I'm going to do is take that enantiomer, turn it into a diastereomer, separate it, and then pluck that piece back off. Remove that chiral resolution agent, remove that original piece, so that I can get my pure enantiomers in separate containers. Cool. That's all chiral resolution is. It's just a way of separating our enantiomers because they have the same physical properties. So I start talking about optical properties. Optical activity is the ability of a chiral molecule to rotate plane polarized light. So I told you that back at the beginning when we were defining what an optical isomer was. I said that it would rotate plane polarized light, and then I was like, just believe me, I'll tell you what that means eventually. Now I'm finally going to tell you. So what that means is plane, meaning a two-dimensional platform, like a plane, one direction. Polarized just means filtered light. So we're going to get all of our light going in one direction, and we're going to filter it out so that it is just all one thing. So when we look at that, we're going to use a polarimeter, which is a instrument that is going to polarize light for us. So we get our light source. Light is scattered. It goes in all different directions, right? Like light goes everywhere. That's how we can see. Then we get our polarimeter, or polarizer, sorry. The whole thing is the polarimeter. The polarizer is this filter. So what that does is that makes sure that only light going in a certain direction can make it through. So now I have plain polarized light, meaning I've filtered the light so that it's only going in one direction. So that plain light comes in, and it is just straight up and down, straight up and down, straight up and down, straight up and down, straight up and down. Ooh, I get to my chiral molecule. My chiral molecule will act as a propeller, and it will literally rotate the light. So it was straight up and down, was straight up and down. Now it's left and right. And then that's what I see out. So here's my little eyeball. I see that light has rotated. So I see this actual light has shifted. Like you see a line that is angled differently than where it would be without your sample. And so then this degree to which it has rotated is your optical rotation, the rotation of light, optics being light. So like if you go to an optician, you're going to someone who's going to tell you about how your eye interacts with light. Your optical rotation is the degree to which it will rotate light. If it rotates the light in a clockwise direction, we're going to say that that is a positive rotation, and we're going to call that dextrorotatory. D-E-X-T-R-O rotatory, R-O-T-A-T-O-R-Y, which gets abbreviated as just lowercase d. If it is going to be counterclockwise, we're going to say that that is a negative rotation, and that is going to be levorotatory. L-E-V-O rotatory, R-O-T-A-T-O-R-Y. And that gets abbreviated that lowercase l. These are not the same as R and S. R and S are that arbitrary signs that were set by Kohn-Engel and Prelog, where it was just the setup of the atomic number, where you're just like looking at it and you're just trying to assign it based on the priorities. So it could happen that the R is D, but R could also be L. D and L are actually based on the whole molecule, how all of the chiral centers together react. So it doesn't matter if you have 40 chiral centers, so it's like R, S, 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 R, S, S, whatever, you will only get D or L because that describes the whole molecule, right? So it's just how does the whole molecule then interact with light. So you don't know that like R doesn't mean it's going to rotate light clockwise. It doesn't mean that. It could rotate light counterclockwise. It's totally an arbitrary assignment by Kahn and Golden Prelog. This has nothing to do with the physical properties. D and L, these are the physical properties. These are actually how did my molecule rotate light. D is clockwise, L is counterclockwise. So those enantiomers, they're going to rotate plane polarized light the same magnitude, but the opposite direction. So that's how we're able to identify if they are enantiomers or not, is we put it into our polarimeter, and if it rotated them the same amount, but different directions, so my R carbone went a negative 61, S went a positive 61, the same magnitude, both are 61 degrees, opposite direction. One was clockwise, one was counterclockwise. R is not always negative. S is not always positive. It depends on the specific molecule, right? So it is totally arbitrary. R and S is that priority based on atomic numbers. The positive and negative is you have to actually observe it. That is, you got to do it in a lab and figure out what the actual value is, right? You can't just look at a molecule and know. You have to test it. That's how you get the plus and minus. That's how you get D and L. When you calculate your specific rotation, that is an intrinsic property. So that specific rotation is going to be uniquely identifying of our molecules. So this is usually a common lab. I don't think OSU does it anymore. I don't think. But anyway, where you actually calculate the specific rotation. So to do that, your specific rotation is represented by alpha. So alpha in brackets is your specific rotation. That is the intrinsic property. Your alpha without brackets is your optical rotation. That is the extrinsic property. That is the actual just observed value. That observed value depends on multiple factors. It depends on temperature, wavelength, concentration, and path length. So all of these come together to determine your optical rotation. And then once you have that standardized, then that becomes the uniquely identifying factor that can be looked up in a table to say, yes, it is truly this molecule. So your temperature is usually in degrees Celsius. Your wavelength is typically identified by the letter D. The D is just associated with the D line of sodium. So if you ever saw those like light separation patterns where like you get the different lines when you do the electromagnetic spectrum, and you see like, if you glow sodium, you see one line. If you do hydrogen, then you, actually hydrogen would be one line. If you do like, I can't remember what any of the colorful ones are, but some of them have like multiple lines, and that's how you can determine like the energy associated with it. Okay, whatever. The point is, the D line of sodium is because sodium lamps are really cheap, they're easy to access. So that means that the wavelength that you're actually using is 589 nanometers. That's what we filtered for, commonly. That's just common. So sometimes you'll see that number, sometimes you just see D. The D is going to be the D line of sodium, is what it's saying. The concentration is usually in grams per milliliter, and the path length is usually in decimeters, which is like the only time I've ever seen the prefix deci used. And so then it's that 10 centimeter little tube is where your sample lives. I do not expect you to be able to do this. The only reason that I still include it in my lecture notes is because I think it's important to understand where these values are coming from, and that you just know that like these are actual, the way that we used to know if a molecule was chiral or not was we literally put it right here and then looked in it, and we just said, does it rotate light? And that's how we found out. That's how we found out about meso compounds as well. Because you put a meso compound in here, and it is not optically active, so it will not rotate the light. It'll come out just straight up and down still. Because the meso compounds are not going to rotate light. They're achiral, not chiral. So you will not need to do any of these calculations. You don't need to memorize that formula. If you need it in lab, they'll give it to you again, but I'm just telling you that's where it comes from. Does that make more sense about the plane polarized light? We cool with that? All right, sweet. All right, so we talked about chirality at the atom level. We talked about chirality at the molecule level. Let's get to the mixture level. So in general, we said that usually if you have chirality at the atom level, then you will usually have chirality at the molecule level, unless you are meso. So that's like the weird exception. So it's like yes at the atom, yes at the molecule, unless you have the internal plane of symmetry, then you're the exception, then you're meso. If you are yes at the molecule level, then you are usually yes at the mixture level. That is usually the answer, unless you are the exception, unless you are racemic. So our racemic mixture, or racemate, is specifically that one-to-one mixture of enantiomers. That is the only mixture that will be achiral, not chiral. So usually, most of the time, majority of the time, you're going to get mixtures of chiral molecules are chiral mixtures. The only way that you are not is if you have exactly a one-to-one mixture, 50% one enantiomer, 50% the other, 50% R, 50% S of those enantiomers, then you're an achiral molecule or mixture. So you have chiral atom, chiral molecule, and then racemic means achiral, you lose chirality at the mixture level. So when we're looking at these mixtures, it becomes useful to report out the enantiomeric excess, the ratio to which we see the R and S enantiomers. Because if it's not a exact one-to-one ratio, if it's not exactly 50% and 50%, then you're going to see rotation. If I put both of these molecules in exactly, that equals 0. Your racemic mixture won't rotate light. If I put just one of the molecules in, if I put just R carbonin, I get the -61. I see rotation. The second that I add that S carbonin, now it is 61 clockwise, 61 counterclockwise. They cancel out. To be that racemic mixture, I see none. So to calculate that enantiomeric excess, how much more of one enantiomer do you have? It is the percent of your major enantiomer minus the percent of the minor. So in the case of a racemate, it is that 50% minus 50% equals 0%. So racemate's EE, enantiomeric excess, is 0 because they're exactly equal to each other. There is no excess. I don't have more of one than the other. That percent EE is also sometimes known as an optical purity, is sometimes how it's said. So you can calculate it in a number of ways. You have one formula, which is that percent of the major minus percent of the minor. That's one way of calculating it. You can also calculate it from your optical rotation. So it is the alpha of the mixture divided by the alpha of the pure enantiomer. So how much did it rotate it if you had 61 and then it like ends up here? So it like pulls back a bit. If this was like pure, you're like, all right, what is that? It is the mixture that you observe over the pure times 100. That would be your percent EE. And then you can also calculate it from moles, where if you look at the moles of the major minus moles of the minor, and then divide that by the total times 100, that also gives you your percent EE. So all three of these formulas are going to be ones that you would need to have memorized. And actually, I'll just be honest, the only ones that I actually care about are that one and this one. We're not going to do moles because moles require actual calculators. So yeah, you're not going to have to use that one. But be aware of the fact that it does work. So those are the two formulas that you want to have memorized in order to calculate your percent EE. Percent EE, personally, I find kind of confusing. Like my brain doesn't readily go from percent EE to then actually tell me how much of each molecule do I have. So I think enantiomeric ratio is more straightforward. That is actually the ratio of the percent of the major to the percent of the minor. It's just, what is the relationship? So my racemic ER is going to be that 50% to 50%, which is 1 to 1. So it's just a 1 to 1 ratio. That tells me that for every 1 R, I get 1 S. For every 1 S, I get 1 R. So I think that that's more straightforward personally, but you need to know how to do both. The process of racemization is an equilibration or equilibrium of one enantiomer to the other. So it is, if you're going back and forth between them, then you end up with a racemate. So you can sometimes start, which this is always really upsetting if you're trying to just get R, and then the R isn't stable. So you make the R, and then it slowly turns into S. Then you end up with a racemic mixture. That's racemization, is one of the enantiomers usually isn't stable, so it'll slowly convert to the other one. It'll equilibrate to the other. So our calculations can also be done for relationships between diastereomers, in which case then instead of it being EE, it's just DE for diastereomeric excess, or DR for diastereomeric ratio. So that's going to be just the percent of the major diastereomer minus the percent of the minor. This would be if you only have 2 diastereomers, then you would use diastereomeric excess, DE. If you have more than 2 diastereomers, which is usually more common, then you would use DR, which is going to be the ratio. So it is just a ratio of all of them. So it would be whatever the percent of diastereomer 1 to the percent of diastereomer 2 to the percent of diastereomer 3, and so on and so forth. Diastereomeric ratio is way more common than diastereomeric excess. All right, so let's practice a problem, an example problem of like, how would we do this? So if I have a solution of plus aniline, and that exhibits an alpha value of positive 4.25, and pure aniline has an alpha value of positive 8.5, then what is my EE? Go ahead and try to solve it. You shouldn't need a calculator, unless you're like me and you don't trust your mental math, but it should hopefully be obvious. All right, what do we get? 50%, yeah. All right, so to do this, we're like, cool, I see alpha values, so that means I'm using this formula, because that's the one I need to find percent EE. This is the one with alphas, so that's the formula that I use. That's the one that I'm gonna plug the values into. So for my percent EE, that is going to be the mixture, which is my observed, over the pure. So 4.25 over 8.5 is half. So that is 50%. Cool? That's how you would use that formula. And that's the kind of thing that I would expect you to be able to do. I would give you whole numbers on an exam to make it easier. So like I would have just rounded it to be 4 and 5 so that it was even more obvious so you don't have to do decimal places. But does that make sense how you would do that? It is your mixture over the pure. All right, so then to calculate the ER, your 50% EE is that excess. So what that means is that you have 50%, stop moving, 50% of my pure positive. How do I know it's the pure positive? Because that's the direction that the majority of it was in. If it was negative, then it'd be 50% pure negative, right? Because this direction is where I get most of it going. Because if it's like pure that, and then my observed is somewhere here, then I'm like, cool, I'm gonna see a positive number because I have more of the positive one. So I know it's 50% of that pure positive and 50% of a racemate, which means that it is 1/2 of the plus 1/2 of the minus. So what that tells me is that this is actually 25% is the positive and 25% is the negative enantiomer. So I actually have a total of 75% of my positive enantiomer and 25% of my negative enantiomer. So my ER is going to be that 75 to 25. You want to get your simplest ratio possible, so divide both by 25 to get a 3-to-1, right? Which to me, I think makes more sense. Like I don't see 50% excess and immediately be like, oh yes, a 3-to-1 ratio. So that's why I like ER better, but you need to know how to do both. EE is the more universally accepted term. Like that's what gets reported out in academic journals. I don't know why, everyone else prefers it. I'm in the minority here. All right. Does anyone have any questions about that? How you would go from EE to ER? And personally, I think this is the easiest way to go to from EE to ER. Like this is the way it works in my brain, is I'm like, all right, this is the excess. So then the other 100% is the racemate. So I split it. So I'm like, half is the one, half is the other, and then group that together to finally figure out exactly how much of that major enantiomer do I have. Cool. Yes? So that is how you would get from EE to ER in general. Yes, so if I gave you, so we could do it again. Here, let's do another practice problem. So calculate the ER for a mixture with, let's make it 33% of the negative enantiomer, whatever it is. And I want the ER reported in positive to negative, because that's usually how I would do it on an exam, is I would put 1 in one place, 1 in the other. So I'd be like, all right, what is the ER in that positive to negative ratio? That's where I'm trying to find the answer. So go ahead and try that same strategy to figure out what your ER is going to be. Actually, let's make it even easier. Let's make it 34%, because I just realized the math works out to be a little weird. So make it 34% so that the other number doesn't require a calculator. and then round. What did we get? A 1-to-2 ratio, yeah. So if I have 34% is negative, then that means that I have a 66% that is racemic. So then that equals 33% is the positive and 33% is the negative. So when I combine those two negatives, I end up with a 67%, or which is about 66, to my 33, which is a 2-to-1 ratio. If you do negative to positive. But I didn't ask for that. I asked for positive to negative. So when you fill in the numbers, just make sure that it matches. Cool. Any questions about that? Yeah. What do you mean? Oh, sorry. So it was the EE. So the EE being 34% negative enantiomer. Sorry. I think I verbally said it, but I didn't actually write it. Yeah, so it was pure, yeah. Yes. So the EE is your enantiomeric excess. So it's actually asking, if you do a 1-to-1 ratio of them, how much more than beyond that 1-to-1 ratio is that excess? So that's why we're saying, like, okay, you have this much is beyond your 1-to-1 ratio. So that is the definition of EE, is saying that if I have like 1-to-1, 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 but then it keeps going on one side, that is my excess. And so then that's the percent that gets reported out. So when you calculate it, 100% is going to be all of your data. So here, let me actually draw what I'm trying to do with my hands. So it's like 1-to-1, 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 and then it keeps going. All of this is 100%. What gets reported here is your percent EE. So then this part is the other half of the 100 is the racemate, because it's the 1-to-1. So that's why it has to be like the other 100% is the racemic mixture. That's the definition of EE. It's the excess of the 1 enantiomer. Cool. Any other questions? Yeah. Yeah, only that 34% is rotating the light. Yeah. Cool. Any other questions? Sweet. All right, so that's all of the content that's going to be on the exam next week. So we are done. That's everything. So if you open up the, where did it go? The graded assignments module, and then you click here for midterms and final exams. That's where you find all of your study guides, and it has everything listed out. Note that the number of lectures covered, that's wrong. So yours are all of our lectures. The other one was for a 2-day-a-week class, not a 3-day-a-week class. It's still the same. I will say I used to never give study guides because anytime I would give a study guide, students would then limit themselves to just the study guide, and they treated it like it was the only thing that they needed to look at. And I don't want you to do that. The only reason that I offer it is because I've just had so many students ask for it that I was like, okay, like, yeah, if you want it that bad, then yes, I will give it to you. So now I just make it readily available. But what I do say is everything that we discuss in lecture is fair game. So how I create your study guide is I opened up the lecture notes and I went page by page and I just wrote down what all of the topics were that we covered. So that's all this list is like the headers on all of our lecture notes. That is our study guide, is just the things that we have talked about. So the specific things that will not be on the exam is anything that requires a calculator. So you will not be expected to use the specific rotation calculation, that big formula that I said where it's like the optical, the observed divided by C over L. That formula you don't need to have memorized. And you won't need to do any EE, ER, DE, or DR calculations that require a calculator, because you cannot have a calculator on the exam. If you bring a calculator, you'll either be told to put it away or it'll be confiscated and then returned to you at the end of the exam. All right? So our general exam 1 content is just chapter 1, 2, 4, and 5. So it is everything from our Gen Chem review to there is also that organic reaction trends is also incorporated. And then we get our structure and reactivity, which is kind of the chapter 2, sort of. The cycloalkanes and stereoisomers. So we need to know our general Gen Chem review. So like what are our ions, what are isotopes, just how we do our electronic structures. The definition of organic chemistry, we are studying compounds that contain carbon and hydrogen. So why is carbon so important to life? It is important to life because it is what gives us our structural diversity. The fact that carbon can make strong bonds to itself and other atoms, and it can make 4 different bonds as well as different types of bonds, or single, double, and triple. That variety, that diversity is what actually gives us our living organisms. That's why carbon is so fundamental to life. We need to know the composition of the atom, that your protons and your neutrons are in the middle, your electrons are on the outside. The key terms that are the ion, isotope, atomic number, atomic mass, reactants, reagents, intermediates, transition state, product, kinetic control, thermodynamic control, all of those words that I said, you need to know all of them, right? So the ion is that plus or minus electrons. Your isotope was that plus or minus neutrons. Your atomic number was the number of protons, and that was always going to be in the lower left-hand corner. Your atomic mass is your protons plus neutrons, and that's in the upper left-hand corner. Your reactants are the things that contain the majority of the carbon compounds, carbon atoms, in your compound, and is usually going to be at the start of your reaction arrow, typically on the left, but it doesn't have to be on the left. Then your reagents are going to be whatever is needed in order to just keep the reaction going, like adding the other elements. Or it could be a catalyst. That is usually written over the arrow, but not always. It could be written to the side. The reactants and reagents together make our starting materials, because it's what you start with. Your intermediate, that was the product of the step. So it is the product, but you're not totally done because you might have multiple steps. So it's the product of one step, and then you go on to the next. Every intermediate gets one transition state. Every step has one transition state. The energy of activation barrier is how tall the hill is. That determines how fast or slow it is. The smaller the energy of activation barrier, the faster. That is your kinetic control, is looking at if it is going to be a smaller hill. The lower the energy is at the end, looking at your product or the intermediate, so the product of that step, if it is lower in energy, that is your thermodynamic control, because lower energy, more stable, that's where it funnels down to. So if you're controlling your product by the fact that you are making more stable product, that is your thermodynamic control. If you are making the product that just forms faster, that is your kinetic control. For our electronegativity and our size periodic table trends, They were just opposite. So it was electronegativity increased as you got closer to fluorine. And then our size increased as you got closer to francium. So as you went up and to the right on the periodic table, that increased your electronegativity. As you went down to the left, that increased your size. Our ionic and our covalent bonds, how do you know if you're going to have an ionic bond? Metal and a non-metal. Don't forget that it's that easy. You see a metal, cool, ionic. For your covalent bonds, that's where you get your two nonmetals. So when you're looking at the bond, you need to be able to identify that bond and then also look at the molecular polarity. Remember, if you are 0.4 or less, including 0.4, then that is going to be a nonpolar bond. Greater than 0.4 makes you a polar bond. And then at a certain point, you get so polarized, you have a metal, you become ionic. So we don't care about that upper limit, because the second you see metal, that's it. You are an ionic bond. We want to have our valency memorized. The valency is related to the standard charges. So group 17 is going to be monovalent. It wants one bond, just like how it forms the 1- charge, like it's F-, it wants one bond. Group 16 is divalent. So oxygen, sulfur, selenium, all of those want two bonds. Their standard charges are 2-. Group 15, nitrogen, wants 3 bonds, and its standard charge is 3-. And then carbon wants 4 bonds. Neutral carbon makes 4 bonds. And so we want to remember our valencies and our octet rule, how to calculate the formal charges. That is your periodic table number of valence electrons minus the dots minus the lines. With our orbitals, remember that your orbitals, your atomic orbitals, are s, p, d, and f. Your hybridized atomic, that's your sp3, sp2, and sp. Then your molecular are the sigma, sigma star, pi, and pi star. sp3 is tetrahedral. sp2 is your trigonal-planar. sp is linear. So we have that quick trick of all single bonds, sp3, double bond, sp2, triple bond, sp, but we need to watch out. If you have resonance, then it can change it. So if you have a lone pair of electrons next to a pi system, then if it looks like it should be sp3, but you're next to an sp2 or sp hybridized atom, you get resonance, then you're going to be an sp2 hybridized atom. So that example being, like if I see that lone pair, that atom is sp2. It looks like it should be sp3, but I have a lone pair next to the double bond, lone pair next to an sp2 hybridized atom, so it itself is also sp2. We want to be able to draw our orbitals. Remember that for your hybridized orbitals, you have that squished balloon look. So your sp3, sp2, why can't I draw a 3? sp3, sp2, and sp all look that where you get the big lobe and the little lobe. You need both. And then you want to make sure that your shading matches when you're trying to draw it on a structure. Bond composition is saying that we have our single bond is made up of a sigma. Your double bond gets 1 sigma, 1 pi. Your triple bond is 1 sigma, 2 pi. The molecular representations, we just need to remember that which ones give us any sort of structural information, and what we assume with our bond line diagrams. With bond line, remember that we are assuming hydrogens on carbon. We assume lone pairs on all heteroatoms. Everything else gets drawn in. Isomers, we have, by the way, I'm doing this all really fast so that on Monday we can just do practice problems. So that's why I know it's kind of whiplash, but also remember this is recorded and all of this is in your notes. But for our isomers, the constitutional, that is where you have the different connectivity. Your stereoisomers have the different three-dimensional shape, but they have the same connectivity. Your conformational isomers are where you rotate a sigma bond. So that was off to the right-hand side of that flow chart, where it was saying our Newman projections, where you rotate a sigma bond. It is the exact same molecule, but it's been rotated, so it has a different energy, so it's called a conformational isomer. Our geometric is that locked conformation, That's where we get cis, trans, E, and Z. Optical is where it rotates plane polarized light. Diastereomers are the relationship between two molecules where you flip some but not all. Your enantiomer is where you flip all of them. All of your stereocenters. For resonance structures, remember that you get that 3 major systems, model systems, where you have a lone pair next to a pi bond, you get a positive charge next to a pi bond, and if you don't have 1 or 2, then you consider 3. So you start with 1 or 2. If you don't have 1 or 2, then do 3. So for the first one, you start at the lone pair and push towards the pi bond, start at the greatest concentration of electron density and push towards the pi bond. In the case of model 2, now that positive charge is lacking electron density, so you start at the pi bond and push towards the positive charge. And we get our resonance arrows always drawn in the middle to illustrate to us the fact that the reality, the hybrid, is halfway between those. It is the average of them. Then if you can't do 1 or 2, then you consider 3. 3 is where you have a polar pi bond. Normal carbon-carbon double bonds do not do this. So don't do it with an alkene. Don't do it with an alkyne. This is only if it is a polar pi bond. Then you can do this charge separation where you can take the electron density, put it on the more electronegative atom, and just separate it between 2 atoms. Most of our resonance structures involve 3 atoms. If you cannot do that, then consider 3, and that can use just 2. But that is not the normal. That is just what you do if you can't do 1 or 2. Then we had all of our different arrows to know, all of that IUPAC nomenclature, as well as the common names and motifs. Remember, alkanes are not functional groups. It is the bare minimum to be an organic compound. So functional groups are the deviation from that. Alkane is what you are to be organic. Everything else on top of it becomes a functional group. So your methyl, methylene, methine, quaternary carbons, those are not functional groups. Your butyl, terbutyl, secbutyl, not functional groups. Those are alkanes. Those are structural motifs. So your actual functional groups, those are like your ketone, your alkene, alkyne, benzene, esters, ethers, the sulfur-containing functional groups. Those are the functional groups. They're the modifications of the alkane chain. We had our acid-base chemistry where we need to know karyo or karye, where it is charge, atom, resonance, induction, hybridization. And we need to have that memorized in that order to be able to apply the relative acid-base chemistry. Our intermolecular forces predicting physical properties, really looking at London dispersion, dipole-dipole, hydrogen bonding, and ion-dipole. Ion-ion's also a thing, but we're worried about polar molecules for the most part, or molecules, I should say. Then we got into our Newman projections for the 3-dimensional conformations. So calculating the energies, looking at the Newman projection. Remember that which column you pick is based on if you are in the Gauss or the eclipsed or the staggered conformation. If you're eclipsed, take the eclipsed values. If you are staggered, take the Gauss values, because that is the staggered conformation. Then we get everything with our chairs that we just recently talked about. So make sure you know, especially for the 6-membered rings, know how to draw a chair flip, know the equilibrium. Remember, up stays up, down stays down, farthest left stays farthest left, farthest right stays farthest right, axial goes to equatorial, equatorial goes to axial. Remember what all the different types of strains are. If you don't remember them, I review them in the recent quiz video. So if you're not sure, the last quiz does all of that. And everything else is pretty much everything that we did this week. So hopefully everything else makes sense. If you have any questions, please let me know. I will stop my office hours next week. Have a wonderful day.